Check it out now. Today's little lesson is on momentum. This virus creeping around like it's a deadly venom. We need a vaccine, scientists working to prevent them. These curves are real, so let's stay inside to prevent them. Welcome back on this brand new day. A new chapter, a new topic, momentum. So, very short lesson today on momentum. If you'll get out the PowerPoint, we'll start and we'll get this jumping. First definition in the slide 6.1, linear momentum. It says that the linear momentum of an object is the product of the mass and the velocity. Product, so we're going to multiply mass and velocity together. So that's pretty simple in the grand scheme of things. The definition for momentum is P. P is little p. Big P was power yesterday. So little p is the symbol for momentum. And momentum is equal to mass times velocity. On the slide it has little arrows over mass and velocity. That simply means that those are vector quantities. We know that velocity is a vector quantity. Remember vector? My name's Vector. I'm committing crimes with direction and magnitude. Well, that's a vector quantity. Momentum is a vector quantity. It has direction and magnitude. So anything that has a mass, in kilograms, the standard unit kilograms, if a problem has grams, you need to convert that to kilograms, times a velocity in meters per second, then it has a momentum. It could be as small as an atom or even a subatomic particle, an electron that has mass. Or it could be as big as a planet or something like that. So anything moving that has velocity, doesn't have to be constant velocity, could be speeding up, slowing down, could be accelerating, regardless. Whatever the velocity is at that given point, the instantaneous velocity times the mass gives it a momentum. I like to use sports as an example, as I've done in the past. Let's use football, for example. Linemen in football, let's say offensive linemen in football that are blocking for your quarterback, tend to be very massive guys. And when they push on a defensive person, they push with lots of momentum. So you rarely see an offensive lineman my size. Doesn't work out too well. I would not have a lot of momentum pushing on somebody with some velocity going forward. So that's momentum. Cars that, let's say you're racing a car on a track like NASCAR, cars that have an incredible speed, let's say 180, 200 miles per hour those cars go, have an incredible amount of momentum. Of course, we could go back to forces. It would take a lot of force to change the momentum of an object if it has a lot of momentum. We'll get into that when we talk about the impulse momentum theorem. An impulse is what changes the momentum of an object, and that's tomorrow's lesson. But I wanted to throw that in there as a preview of where we're going with that. So really, it's pretty simple. You just multiply mass and velocity together, and the actual unit for momentum is a kilogram meter per second. So there's no special name for that, like there is joules for working energy, or newtons for forces, or watts for power. There's no special name for a kilogram meter per second. I always thought maybe a mho, we could call it a mho for momentum. 20 mhos of no, maybe. That might catch on with this video. But we'll call it a kilogram meter per second. So if you're reading a problem and it says the momentum is, like I said, 20 kilogram meter per second, you see that unit, go, oh, well, there's the momentum right there in that problem. So I'm going to plug it in right here where momentum goes. So that's all the first slide says, is that the linear momentum of an object is the product of the mass and the velocity. And it gives you basically what I just said. Note that momentum is a vector. It has both magnitude and direction, and the unit has no special name. So literally what I just said in the video here. We're going to do some problems in just a second. You have some homework problems. It says to do all of them, and just like the power problems, there's only 6 problems. I'll do the last one because the last one is a little harder than all the other ones, and you have to find the velocity in that problem. And I'm going to show you 2 different ways to do that in that problem. One you could do by kinematics, which you know how to do. If that's what came to your mind, you're like, oh, I can do that by kinematics. The other way is by changes in energy, which I told you had no problems in to do for conversions of energy, but I'm going to show you how to do it that way also. The next slide basically says this, that for a system of objects, the momentum is the vector sum of all the individual momenta together, momenta being the plural of momentum. So the example I used yesterday was pool. I used pool in the conservation of energy, kinetic energy, but we could also use pool as an example for momentum as well. So you give a cue ball some initial momentum. So the cue ball has a momentum as it goes down the pool table, and it hits all the other balls. If you're playing 8-ball, let's say they're in a rack like this, and the cue ball hits it, and all the other balls go spreading out all over the table. Well, if you added up the individual momentum of each ball, the sum of that would have to be equal to the momentum you started with. So it's like energy, and we'll talk about conservation of momentum later on, that you can't lose or gain momentum. You can't have more momentum in the end than you started with. Bowling is another good example. I like to bowl, not real good at it, but it's fun. If you have a very massive ball, let's say you're pretty strong and you use one of those 16-pound bowling balls, and you can throw it with a great velocity, so you rear back and you chunk it down the lane, well, that ball has an incredible amount of momentum as it's going down the lane, and when it hits all the pins at the end of the lane, all of the momentum of that ball is transferred into the pins. Well, I shouldn't say all. If the ball continues to go forward, then it still has some momentum, but it loses a lot of its momentum, and it's transferred in those pins. And the pins go like that, and they explode. Not literally, but figuratively, it sounds like they do. However, if you use a smaller ball and you're not quite as strong, the pins kind of do this. They go bloop and fall over like that. So that's a good example of two different momenta. I used the example of a Ferrari and a Toyota Camry yesterday. Ferrari probably pretty lightweight in relation to a Toyota Camry, but the Ferrari would have a lot more velocity in a short amount of time, so it would have more momentum. But think of a train and a car. A train having an incredible amount of mass and a velocity if it's moving, versus a car who has much less mass and let's say the same velocity as the train. Then the train would have an incredible amount of momentum. It would take an incredible amount of force to stop the momentum of that train. Additionally, it would also take a lot of force to start the train moving to give it a momentum. So all of this is tied into what we've been talking about up until this point. Kinematics, motion itself, acceleration associated with kinematics, the changes in motion, forces that cause that changes in motion, work, that force that acts through a displacement that causes changes in energy, conversion of energy from one form to another, and now momentum, the changes in momentum or the momentum of an object. So really, I told you day one in this class that this class is a building process, and everything we talk about every day builds on concept after concept after concept. So here we are with momentum, and we'll talk about some collisions, types of collisions in the next day or so. But let's jump into these problems. By the way, we're not going to do a problem where you have to resolve a whole bunch of momentum vectors, because you could resolve momentum into components. For example, in my pool ball example, if this is a pool ball headed this way, and let's say it hits another ball, and that ball goes that way, and the cue ball goes off in that direction, then the components of these could be resolved to see what magnitude and direction that those components have. I'm going to save you that. We've done enough resolving with vectors so far. We're probably going to stick to one-dimensional momentum problems. Maybe if we get back to school in a regular amount of time, in some amount of time, maybe we can do some two-dimensional momentum problems. But we'll save the one-dimensional for home. So, like I said, there's going to be a short lesson, but let's do a problem right quick. I have a problem number 6 on the problems that you're supposed to be doing today pulled up. Oops, that's the answer key. There it is. Number 6, this would be the one that says problem A, momentum. Number 6 says this, that in 1994, a tower 22.13 meters tall was built of Lego blocks. Suppose a block with a mass of 2 grams. Well, that already tells me I need to convert in this problem. If it's 2 grams, is dropped from the top of the tower, neglecting air resistance. So this is a good one. We're not going to count in air resistance. We're going to assume this is in a vacuum with no air resistance. So it's dropped from the block of the tower. Calculate the block's momentum as it hits the ground. So what do we need to find momentum? We need 2 things. We need mass. Well, we already know the mass of the block. It is, excuse me, the mass of the block is 0.002 kilograms, which was 2 grams. So I had to convert that into kilograms in order to get the right answer. So move my decimal place 3 places to the right, and that gives me 0.002 kilograms. I need to know the velocity of that block the moment it hits the ground. How fast is it going the moment it hits the ground? Well, let's draw a picture here. It says the block was dropped, the Lego block was dropped from the top of the tower, which was 22.13 meters high. We're assuming that initial velocity it was dropped with was 0, that it had no initial velocity. And we want to know, well, what's the velocity of it when it hits the ground? If we knew the velocity when it hit the ground, then we would know how much momentum the block had when it hit the ground. So you're probably looking at that going, I can do that by kinematics. That's just a simple kinematic situation, that if I know let's write out our variables and see what we know. So there we are, initial displacement final, initial velocity final, acceleration in time. This is one of those frame of reference things. I'm going to call my initial displacement 22.13 meters here above the ground, and I'm going to call the ground level 0. So it ends on the ground that I defined as 0, therefore it started above that, a positive number. The initial velocity was 0. Don't know the final velocity. Acceleration is due to gravity, negative 9.81 meters per second squared, and I don't know the time. So I want to know what's final velocity. So it looks like that v squared formula, the one that I derived the other day for acceleration. So if we use that v squared formula, that should give us the final velocity. So v squared is equal to initial velocity squared, which was 0, plus 2a, negative 9.81, times change in displacement, final minus initial, well, that's 0 minus 22.13, so that'd be negative 22.13. So if I multiply all that out, 2 times 9.81 is 19.62, times 22.13, I get v squared is 434.19, and then if I take the square root of that to solve for v, I get 20.84. So the final velocity is 20.84 meters per second. But remember, which way is that block going when it hits the ground? It's going downward, isn't it? So let's give it the correct direction. The correct direction would be headed downward, so negative 20.84. So the final velocity of the block as it hits the ground is 20.84 meters per second. And So there's our final velocity. So to find the final momentum of the block, just multiply them together. But this is something neat, that this took a little effort to find this. Not a lot. You've done one-dimensional kinematics before. That wasn't too hard. But could we find that in terms of changes in energy? So check this out. This is a really neat thing. What kind of energy did that block have initially before it was dropped? Think about that for a second. What kind of energy did that block have the moment it was about to fall? It wasn't in motion yet, so it had an initial velocity of 0. What kind of energy did it have? I'm sure you got it. It had gravitational potential energy only. So if we said energy is conserved, if there's no non-conservative forces in here, and we know there's non-conservative forces because the problem told us it took friction away, no air resistance, so the only force acting in this system of objects, the system being the Lego itself, was gravity. And we said yesterday that gravity was a conservative force. It's going to allow energy to be conserved, 100% of it, if energy is conserved. So what's the formula for gravitational potential energy? Mass times gravity times height. Well, as that block falls, what is it losing? If it's losing height, it's losing gravitational potential energy. But in turn, what is that gravitational potential energy being converted into? Yeah, it's being converted into kinetic energy. So as it falls, it's losing gravitational potential energy, but the moment it hits the ground, it's got kinetic energy, only kinetic energy. So if it's a closed system, no non-conservative forces, isolated system, I use that term also, then all of this gravitational potential energy has to be converted into kinetic energy the moment it hits the ground, because it's at 0 height now. Mass times gravity times 0, last time I checked, was 0, so it has no potential anymore, and the formula for kinetic energy was 1/2 mv squared. So in that case, what's going on initial? What kind of mechanical energy did this block have initially? It had potential only. So it had gravitational potential. Well, that's got to equal all of the final mechanical energy. Hopefully you remember what mechanical energy was. It was the sum of all kinetic and the relevant forms of potential energy. So right here, let's add them up. See, I got gravitational potential energy and no kinetic, no elastic potential. So only thing it has initial is gravitational. Well, what about when it hits the ground? What kind of mechanical energy does it have? At that moment, when it's final down here, has no gravitational potential anymore, has no elastic potential, but it's got kinetic. So this is conservation of energy, that all of the initial energy, mechanical energy, has to equal all the final mechanical energy. So the only kind it had initially was gravitational, the only kind it had final was kinetic. So if I put the formulas in here, then mgh has to equal 1/2 mv squared. Well, looks like if I divided by m, it doesn't matter what the mass was, because in a vacuum, all objects are going to accelerate at the same rate, -9.81 meters per second squared. Doesn't matter if it's a Lego block or a bowling ball. They're going to accelerate downward at the same rate. So looks like the masses would cancel out if I divided through by m. And let's plug some numbers here. Gravity is 9.81. You could put negative in there. Height was 22.13, is equal to 1/2 v squared. Well, I can multiply 9.81 times 22.13. 9.81 times 22.13 is 217.09. So 217.09 is equal to 1/2 v squared. Well, let me multiply 2 over here to cancel it out there. Times 2 is 434.19. 0.19 is equal to V squared. And then the square root of that number gives me 20.84. 20.84 meters per second is equal to V. Does that answer look familiar? The same answer I got using kinematics. Of course, it's still negative. The direction is still downward when it hits the ground, negative. And so I found the final velocity using kinematic equations. I'm sure that's how you would have done it if you would have done this problem on your own. But wasn't it easier, or just as easy, to do it by changes in energy? That the only energy was potential to begin with and kinetic final? And keep in mind, that's only if this is an isolated or closed system and all of the energy is converted. Throw a non-conservative force in there, and what are you going to get? Throw in air resistance, you're going to get less kinetic energy final than you would have initial. Now, you could figure that out. You could figure out how much work was done by air resistance by finding the difference and finding what was lost to the environment due to a non-conservative force. So I know that's a lot that I just threw at you, and I told you we were not going to do conservation of energy problems, but I just wanted to show you how it worked because I did mention it yesterday in my conservation of energy video and show you how easy it is in comparison to kinematics. They're both easy, really, if you understand the concept. Well, let's get an answer here. So 0.002 times negative 20.84, and I get negative 0.04 kilogram meter per second. So there's the final momentum of that Lego block when it hits the floor from 22.13 meters above the ground. When it hits the ground, it has negative 0.04 kilogram meters per second worth of momentum. Not a lot of momentum. I don't think a Lego block hitting you on the toe is going to hurt that bad. If it was a bowling ball with a lot more mass, it would have a lot more momentum when it hits the ground. So there's your answer. I think the other problems that you have to do are easier than that one. I don't think you have to find final velocity in the rest of the problems. Maybe number 5 you do. I can't remember what it said. But so not a hard concept. So this is the first concept in this chapter. So be sure you understand the concept of momentum, because tomorrow when we talk about the impulse momentum theorem, we're going to add something to this. We're going to add force to this and see how forces change the momentum of an object, just like they change the velocity of an object. They cause objects to accelerate, and also how they change how they do work on an object to change the energy of a system. So a lot of stuff here, and I told you in the very beginning of this class, when you did that one-dimensional kinematic test, the one you thought was really hard, where you use the kinematic equations and you're like, oh, this is the hardest thing I've ever done. I told you it's going to get harder. So based on your frame of reference now, that test was probably pretty easy in hindsight. But y'all stay safe out there. Do your work. If you have questions, be sure to shoot me an email, or you can send me a message on Remind. I have students sending me answers to their problems, and I'm checking them. You can send them at any time, even after 4 o'clock in the afternoon. It doesn't matter. Try not to do it too late. I'll be sacked out by 10 o'clock or so. Yeah, I do go to bed pretty early, but I'll sure to respond tomorrow morning if I don't get it till after then. So hope to see you soon. Work hard and stay safe.